Hello and welcome to Sean White's Solar and Energy Storage Podcast. Today, our very special guest is Paul Frischer, and Paul is the president and head of technology at GO-OPV. And welcome to the show, Paul.
Hi, Sean. Nice to meet you. Great to be here.
Yeah, very good to meet you too. And it looks like what we're going to talk about is something called a printed semiconductor. In fact, when I first learned about you, I wasn't even sure if it was solar. I was just like, somebody was telling me like, oh, there's this guy you got to talk to, and it's something about printed semiconductors. And I was like, well, it sounds like thin film, but I'm just not 100% sure. So maybe you could tell us a little bit about your product, which is pretty cool just from what you've been showing me just now.
Yeah, so I think that in the market today, people are most familiar with PV structures, or they're comfortable with wind, or they're comfortable with hydro. So they have terminology and different kinds of energy sources. But printed semiconductor actually novelly comes from fossil fuel. And so when you consider that and you say, well, wait a second, what does that mean that it's coming from a fossil fuel? The reason is that it's organic. And so when you look at an organic structure, we're completely not related to anything associated to what you commonly refer to as a silicon semiconductor, because that's an inorganic process. Our
Maybe we could
process.
talk about like chemistry class and what organic means. And so from what I remember from chemistry class, like I took an organic chemistry class, which at UC Berkeley, which was the most difficult class that I ever took. I thought I was going to fail. I got like what I thought was a terrible score, and it was a B plus. So, and so organic pretty much means carbon based. So us humans were carbon based, and dinosaurs were carbon based. And I think they say that most of oil was some like cycads or like these old plants from millions of years ago. But anyway, oil is what was once a plant mostly, and maybe a couple of dinosaurs in there, from the time of those brontosauruses and the Flintstones. So organic, carbon based, and then we have silicon, and that would be inorganic, even though it's very much like carbon. And silicon is right underneath carbon on the periodic table of elements. And carbon and silicon each have 4 out of 8 electrons filled in the outer shell. And they're really good at attaching to different things and making crystals and different things like that. In fact, one interesting thing about the Earth's crust is the second most abundant element in the Earth's crust is silicon. So we're never going to run out of silicon. But also, we know that there's carbon all over the place. We're breathing it out of the air, or it's in our bodies, and it's in these super awesome solar cells that you're going to tell us about.
Yeah, so what happens is that's always the immediate response that we're talking about solar cells, which is an interesting construct. So when you think about that, you would always refer to a silicon cell that's produced by actually introducing carbon and then doing it at this insanely high temperature in order to remove the oxygen from silica. And then that would give you silicon. So that's this inorganic side. And that's also similar to when you're making metals, right? So you've got iron and you put carbon in it, and then that's adding oxygen into it, and you make steel. So you have this entire inorganic side. But on the complexity side, you look at organic. We are organic, as you mentioned earlier, DNA, RNA. And so the idea is that if we can make a zero emission, and that's the key here, as opposed to burning the fuel. So when you think of fossil fuels, you think of burning the fuel, right? That then moves a turbine, that turbine then moves a generator, and that's sort of the classical from 1800, however you want to look at it. That's the methodology. But if you had the way to actually use carbon as a zero emission way in order to produce power, which is what orange printed semiconductor actually does, now that would be the greatest thing in the world, right? That would be, oh, so we can make power zero emission, but we can actually do that carbon based. And I would love to say that I invented it, but I didn't. The actual invention is by 3 brilliant physicists. I would assume that's what you would call them, Proto, Curl, and Smalley. And they're the ones who took graphite. So just think about what's in your pencil, simple graphite, and they pulsed it with a laser in an environment that had helium. And so there was no oxygen there. And it did what's called the vaporization or a partial combustion. And when that happened, That was a revelation in 1985 that we actually could produce nanoparticles. It was called fullerene.
In 85. And so graphite's carbon, like in a pencil or something, I guess.
Mhm.
And then they just blast it.
They blast it with a laser and they put
Uh,
it in an environment where there's no oxygen and it partially combusts, means you get soot. And from there, you ended up with C60, which is carbon 60, which actually looks like a pickleball.
Carbon 60.
Yeah, C60.
What does that mean?
It's a linkage where you've got carbon with 60 different connection points to create this circle.
Wow. So it sounds like what, like a Buckminster Fuller type of thing?
That's exactly what it is. I'm glad you had the term.
So a Bucky ball. So Buckminster Fuller was some kind of like crazy genius that people were making domes, I think. And then he made some kind of thing called a Bucky ball that was
Yes.
like some way of making an atom so it's a circle or like a sphere, I guess. Yeah.
That's exactly correct. And now it's at the nano level. And so what they realized is that fullerene is a fantastic absorber of electrons. So now you have this organic material that you've created from graphite.
And it's called fullerene after Buckminster?
It's fullerene. So the actual, I guess, periodic table, or however you look at it, whatever the nomenclature is C60. It was the first nanoparticle derivative of carbon that could absorb electrons, which was the pathway to create organic printed semiconductor.
Wow, that's pretty cool. And so I guess what the 60 is for C60, I just was thinking that was too big of a number, but it's 60 carbon atoms making a sphere. Wow. Okay.
Yeah, so when you think about the architecture now, and you think about the complexity, it's always been known this is theoretical. And now in 1985, the world changes. These guys received the Nobel Peace Prize or Science Prize in 1996. So yeah, so what ends up happening is we end up with C60. So we've now got fullerene. And what happens with fullerene is now what you need is you need what we would refer to as a donor. And so when you think about the donor, if you look at an OLED or an organic LED television set, or you look on the ink on your phone, on your cell phone, there's donors that basically supply the electrons to the fullerene. And so now you've created this printed semiconductor.
So are all those things using the C60, the TV and the phone screen and
They're
all that?
not. They're actually using something called, they refer to it as P3HT is typically what they use is P3HT.
Oh yeah, I got a bunch of that in a jar here in the spice
Yeah,
cabinet.
so there's all the technical terms, but essentially in order to create an organic semiconductor, you needed the acceptor or the absorber. And so once fullerene was developed, you now had the absorber. And so there was billions of dollars, as I was trying to explain earlier, that were invested. Once 1996 came, billions and billions and billions of dollars was invested into the industry. And you had probably the single largest company called Canarca. And Canarca was a collaboration.
So when you say billions into the industry in the 90s, this probably wasn't for solar because the solar industry was too small at that time.
Yeah, the billions of dollars that came in was after 1996, as solar was generating. By the 2000, people were now recognizing that if there was a way, in order at the nanoscale to use the fullerene as a zero emission power source and heat gain reduction solution, that would basically eclipse all energy. It would be the AI of the energy business.
So in the 90s, they were spending billions on this
They
technology.
didn't get to the billions until early 2000.
Oh, so even in the early 2000s, that's interesting that they were spending billions on organic solar technology.
Yes. And then
Okay.
in 2012, Canarca went bankrupt, and all of the other companies that were looking to make printed semiconductor went bankrupt, and it was a huge implosion of the industry.
Would you call all thin film printed semiconductor?
Yeah, so that's a misnomer as well. So thin film relates totally to silicon or amorphous. So that's a different category.
What about First Solar?
Yeah, so First Solar is CDTE. That's a thin film, what you call solar type product,
Uh-huh.
versus what we produce, which is printed semiconductor and flexible PET plastic.
Okay. So, but would First Solar also be called printed semiconductor?
No, it's not a printed semiconductor.
Oh, hmm. Okay.
So where we end up is we end up in a interesting format that what we're doing is a printed semi-transparent material that's roll to roll processed on PET plastic. It would be entirely different than what the processing would be that someone like First Solar would do.
So PET plastic, is that polyethylene? Is that what PE stands for? I'm not sure.
Yeah, so you've got polyethylene tetrahydrate, which is essentially a water bottle. So when you think about
Okay. Hmm.
every single water bottle that you've ever seen in the world, all that material that's in the world, that's actually also an organic product. And so what differentiates what we're doing is that we can actually do roll-to-roll processing of layers of what's basically a donor material and then the absorber, which is the fullerene. Then we can have an anode and a cathode. We can capture the movements of those electrons. And we are the first company, and I believe the only company at this point that has ever commercially produced this material.
Cool. All right. Great. And so you just go out there and get a, is it an inkjet printer or a laser printer you're making it with?
Yeah, so that's really cool. So it's conventional printing. So you have all the conventional printing machines, which are either coding for slot die and spin die, or you have screen printing and gravure printing. And so you're using all classical different ways of printing equipment, and then each of the different layers of what you need in terms of the organic construction of the material itself. You have different printers that do different print heads for different layers.
Great. And so they're pretty much just printing out the P layer and the N layer, and you got a PN junction and all that kind of stuff.
Yeah, so when you think about it, think about a newspaper printer or think about your laser printer, right?
Mm-hmm.
Think about the idea that you can actually print power as if you were printing newspaper.
Uh-huh.
The power that's being generated is zero emission, right? And it's also absorbing the heat gain. And so I'll give you some metrics to think about this for a second in terms of carbon. So you mentioned earlier, oil and petroleum. So think about a tank of gas, right? So if you had a tank of gas and you had a gallon of gas, that essentially could produce 33 kilowatt hours, okay? Or you're
Yep.
driving about 6 miles,
Mm-hmm.
right?
Yep.
And when you consider the nano level of what we're doing in terms of how it works, you could take 1 liter, which is about a quart, but 1 liter, okay, of the fullerene material in today, what we're doing now. You can produce 100 square meters. Each of those square meters produces about 50 watts. So one small jar of material now gives you 5,000 watts of potential power. Imagine that you now do that 1 hour for 365 days, gives you about 1,800 kilowatt hours. And the material is set to last for 10 years. So if you do that for 10 years, you're going to produce about 18 megawatts of power. So think about the two things now. Here you have your car, and you've got your tank of gas, and you've gone 6 miles, right? And you
Mm-hmm.
produce approximately 6 kilowatts. And we're going to use that same amount of material, and we're going to produce 18 megawatts,
Or is that megawatt hours?
megawatt hours.
Yeah. Okay. Great. Awesome. And you also mentioned that it is, you get about 50 watts per square meter. So that would be like 5% efficient. And I also noticed too that you're using it in applications where it is semi-transparent, like for windows and things like that.
Yeah, that's exactly what makes it so interesting is that it's semi-transparent and that it absorbs heat gain. And so that was the link to two developments of where the company really went to. The first one was that we were able to commercialize it, meaning that we were able to make material that produced enough power to be competitive in the market, as well in a semi-transparent form, which meant that we could actually apply the material inside the building. And so for the applications, we realized we don't need to be on a rooftop, we don't need to be outside, but we actually have the light absorption so that the film itself can actually reside on the inside of the building. And so with that differentiation, that created a whole new way of creating power on site and coming up with different ways to do the distribution.
Okay.
And so what is really important in that discussion about the efficiency is that printed semiconductor does not functionally work like silicon. So people immediately go to, okay, what's the efficiency of a particular material? And so when you're trying to compare a coal factory versus a gas-fired power plant, so you got a coal power plant and a gas-fired, you'll compare them on MMBTU. Once we developed a commercial version of printed semiconductor, you needed a way to compare the efficiency between how much power is put by an organic printed semiconductor versus silicon. And that became total harvested power. So that's a really key element of this discussion is what total harvested power is, because the way an organic printed semiconductor is, we are the tortoise, silicon is the hare. So you have one point, like a TP, where silicon is going to make power. Organic printed semiconductor makes power like a plateau. And so once the power goes on, it makes power throughout the entire day. And so when you compare 1 watt of printed semiconductor against 1 watt of silicon, we actually produce 30% more power on a watt per watt basis.
So is that because, well, for one thing, they just talk about standard test conditions with when they test PV, but another thing would be perhaps your technology is absorbing more of the spectrum of light?
It absorbs more of the spectrum of light, and so therefore its overall efficiency in terms of making power. So you have low light conditions, you have medium light conditions, and you have high light conditions. We're able to produce that optimized through the entire segment, where silicon will only make power when it's at the peak level in the middle of the day.
Cool. And one thing I noticed too that you were showing me before we started is you had this cool thing that was like a blind. So it just rolls up like some blinds do. And you actually had a button under your desk, I think, something like that. And it was like going up and down over your bookshelf, but people could put that, of course, over their windows. So that was just kind of neat too. It's like you can make blinds out of this stuff. I should get some. I've got a window here that needs a blind.
Well, thank you for the segue to that. Yeah, that is honestly, we have not been out in the market for a while with all of our innovation, but our first lead-in product that we'll be introducing for 2025 will be the relationship with MecoShade. MecoShade has the leading commercial line of product called ElectroShade. We knew that printed semiconductor can do over 50,000 wind-ups on a roll that's, let's say, 120 millimeters. And so 3 years ago, after Meco had seen some of our installations where we were actually mounting the film on the window itself, we put together a collaboration and said, this is actually something that we could do that no one else in the world can do, and that is to make the first organic printed semiconductor shade. And with Meco's engineering in the ElectroShade product line, we actually can make a double roller, which is pretty unique.
Cool, cool. And so for that application for the blind, are you looking at grid tie solar or some other application?
Yeah, so that's great. In terms of you're typically using in what your conventional solar systems would be is an inverter. And we don't have any inverters in our system. Everything that we actually drive is direct DC. And people go, well, why are you driving direct DC and you don't need to have an inverter? And the explanation is, well, we have systems like power over the Ethernet. So power over the Ethernet is a way to distribute power that you can have data transmission as well as power in low voltage DC systems. And you also have a situation where we're going to use lights. Let's say you're using an LED light. Your LED light is going to be driven by direct DC. Your computer is going to be driven by direct DC. Your phone is going to be driven by direct DC. So imagine now that we put a shade that has the organic printed film, shades in the window. When the sun is out, you're now able to produce power. That power can now be distributed within the environment that you're in, and everything can be powered by that from the standpoint that your lights, your phone, your computer can all now be powered by zero emission on-site power in an automated shade.
Great. So are you looking at DC microgrids and buildings and things like that, I guess?
Yeah, so that's our structure. Our structure is DC microgrids within the buildings. Everything has what we would refer to as distributed battery storage, as opposed to the large bank batteries that you traditionally would use. We use 9 amp hour distributed battery systems. So you use the power and the storage where you need it. And then the flip side to that, and this is sort of the biggest piece about the shade. So the power side is really exciting, and so is the storage. But when you look at heat gain reduction is 30 times effective than actually generating power, meaning that even if you made 1 watt of power, the fact that we're able to actually absorb and reflect the heat gain coming from the sun through the window, the actual savings from that is 30 times as much as actually generating 1 watt of power.
Great. Yeah. So I think they might call that passive solar too, where you're just using creativity to do things like block the sunlight and at one time of the year, or maybe let some in at the other time of the year.
Yeah, so there were technologies that were developed, like you had an insufilm or you had electrochromatics, you had different technologies in terms of, I'll use the word blocking the sun from coming in, but then you lose the transparency of the window. And
Mhm.
so what's unique about this is that you always have the opportunity to have the transparency of the window. You then get the heat gain reduction. So from an organic printed semiconductor, from orange, as we would call it, so it's orange with an E, you end up reducing the temperature between 6 and 8 degrees in the environment as a result of what we would call the solar factor reduction. So if you
Yeah.
had 100% of the heat coming in, now only 30% of that heat would actually pass through into the environment that you're in.
Yeah, I often think of that when on the hotter times of the year when the sun is like beating in the window and it's hitting where I live. It has a dark colored floor. And it's like, standard test conditions is 1,000 watts per square meter. So with big windows and things like that, it's like I have a whole bunch of heaters turned on.
Yeah, that's exactly right. And so where we now have the materials, we have the material is in skylights and malls, we have it in windows and offices. And so now releasing the shade, meaning introducing the shade with Mecco, now gives us the opportunity to go everywhere in what I'll call the built environment. So if you think about New York City as an example, where they have LL97, uh, given that they already have the pockets set up for the shades of whatever motorized shade that they had previously, this is an opportunity to use the electroshade parts and equipment, the Mecco know-how, Mecco solar track, the introduction of the orange printed semiconductor, and now you could basically retrofit every single office environment in every major city in the US and in the world.
Hey, I got a question for you too. Does the power from the sun open and close the shade?
Yes, so that's a
Mhm.
great point. So the answer is yes, it's self-powering. And not only is it self-powering, but the additional power that we're producing is the power that can now be used to turn on the lights in order to charge your phone, in order to charge your laptop.
Just that fact itself, where you just don't have to wire up your shade, is pretty cool.
It's massive savings when you think about the idea that you would normally have to bring either on the electrical side, wiring to come all the way to the shade, which is extremely expensive. And so we made the shade work in 2 different ways. One is a self-powered version, which it does exactly what you're saying. It creates its own power in order for the shade to go up and down. And then it also has an interconnect because Mecco has a group that is creating DC micro networks, and those are driven off power over the Ethernet. And so what we're able to do is go into a unit called a node, and that particular node takes the low voltage DC power and then can redistribute it into lights and sensors and anything that you want to do in the built environment. And so what we're able to do then is take the excess power that's produced by the orange electric shade, we introduce that into the DC network, micro network, and now we can push power wherever we want in terms of different places and different uses within the built environment.
What kind of voltage are these devices? Because I know that a lot of non-silicon solar is known for having high voltage, and it's just how they arrange the connections in the cells within the module. So is yours more coordinated towards charging like a single lithium-ion battery?
It's a good point. So one of the big differentiators between what you call classical or traditional or conventional solar is they're putting modules in series and they're running very high voltages. And it's a pretty dangerous environment. And so therefore you have to have inverters and breakers and switches because you're running 600 volts. That's not an
Mhm.
optimizer. What we do is we channel this to 24.5 volts. So under the National Electric Code, anything that's under effectively 50 volts enables you to be what's called class 2 or low voltage. And for PV systems, so if you're generating the power by PV, the system has to be below 30 volts so that you don't have to have what's called a shutdown switch. So all of the RNG systems all have 24.5 volts. Everything is connected in parallel. We go to the maximum amount on the class 2 in terms of 100 watts. So every system can effectively be 100 watts running at 24.5 volts, and we can have as many systems as we want in the built environment.
And so what is the voltage of the battery? Because what did you say, 9 amp hours?
So 9 amp hours, you bring a great point. So in order to distribute the power, we selected power over the Ethernet because that gave us the opportunity to do something that we thought was pretty cool. We could actually have three different inputs going into what we would refer to as a switch. So in the lingo of what you would refer to in terms of networks, a switch can either just push data or the switch can actually push power and data. So when it's pushing that, it's called PoE. So we created a switch, a PoE switch, that can actually have a 12-volt battery. We can actually bring in the grid, as you refer to it as the grid, but we don't go back into the grid. We can bring into the grid and we can use a converter that essentially converts the power from the grid from AC to DC. And then we bring in at 17 to 18 volts and then we bring in the orange film power at 24.5. We combine all of those voltages together to come out with a constant voltage of 48 volts that's then distributed across the Ethernet cable.
Okay, so you got 48 volts. Is that what power over Ethernet is 48 volts?
48 to 53 volts.
48 to 53 volts. All right. And then when you are going to go do something with that power that's coming through the Ethernet, like what do you charge a phone or something like that?
Yeah, so what happens is now you have this ability to move 90 watts of power through an Ethernet cable. So every
Oh,
building pretty
okay.
much in America has already been pre-wired with Ethernet cable.
I didn't realize that Ethernet cable could bring you a whole 90 watts.
So that's the innovation. So they started out with what they call 802 AF, AT. Now we're up to 802 BT is the standard. 802 BT standard enables you to move 90 watts. You can move it over 330 feet on the cable. And if you add coax to it, you can actually go another 3,000 feet and reconvert it back into PoE. So the PoE space is really now emerged as not only power, but it's got all of the data. So think about your office now that you have a hub that now has power and data. You can sense all the humidity, you can sense how many people in the room, you can sense the temperature, you can sense every single thing that's actually happening in that environment. You're using a zero emission source of power. You're reducing the heat gain in that room by 6 to 8 degrees. And every device that you have within that environment is now running on DC. This is a very, very, very efficient way in order to run your building.
We interrupt you for a very important announcement. Sean White's Solar and Energy Storage Podcast has been brought to you by Sean White's Solar and Energy Storage Podcast. That's right, Sean White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSean, that's solar, SEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show. So everybody always makes jokes about your solar works at night, but does your solar work at night? I mean, you're in a building, the blinds are down. I know that a calculator that's solar powered works at night. Is it doing anything like somewhat significant or?
So, does it make power at night? If there's any light source that's available, then the organic printed semiconductor is going to make it. The alternative, obviously, is that we have 24/7 running systems on the fact that every system has the ability to run off battery storage, and alternatively, the grid interface that's coming in at a DC convert.
Okay, great. Yeah. And then I also know that there's a lot of talk about different types of USB-C cables that could deliver more significant amounts of power. Do you know anything about that?
Yeah, so that's an interface that we do. So we actually literally take our material, we can put it into USB-C, we do it in USB-A as the power source for that. What makes organic printed semiconductor, orange, so special is that you don't need outdoor light. So think about it this way. Printed semiconductor works on indoor light, low light, it works on medium light, it works on any light source whatsoever. And it works at any angle to the light. So you don't have to be perfectly tilted to the light or to the sun in order to make power. What fullerene did was great. What really happened was in 2018 was the invention of non-fullerene. Non-fullerene meaning that you're no longer limited to the C60. And so what a non-fullerene became is, if you take naphthalene as an example, the PhDs and the scientists were able to figure out that there are other organic-based materials that they could create that could also be absorbers. So there was a theoretical limit to how much power you can make with fullerene. Now with what we refer to as non-fullerene, not meaning that they're not organic, but that they're non-fullerene, we've already hit most recently 20.8% efficiency. There's theoretical conversation that we can actually go to, let's say, 44% efficiency. But just to put it in scale,
okay,
if you have 1.65% efficient printed semiconductor, organic printed semiconductor, that equates to 12.5%, as you would call inorganic or silicon. So why were we commercially successful? We were commercially successful because we were able in our first iteration to bring orange to 3.5% efficiency, 3.5% efficiency being surpassing 22% silicon. And so now when we look at non-fullerene, which is why we were talking earlier, that you can get to 4, 5, 6, these numbers now can reach 20.8% efficiency as noted. And that happened in 6 years. Think about where we're going with this. That happened in 6 years.
So you said non-fullerene is called naphthalene?
No, an example of how you could make a non-fullerene would come from naphthalene. So they're still all fossil fuel based.
What is naphthalene?
It's from the petroleum oil. It's a derivative of the petroleum oil. So when
Is it something they make soap with, or
I
know,
don't know, that's beyond
and
my.
like I know there's some kind of like poison oak soap called Fells Napth, and it sounds kind of familiar, like in the back of my head. And I grew up around poison oak. I'm pretty much immune to it.
So what we've discovered is that from petroleum, from carbon-based materials, we can make much, much more complex systems. And so when you compare us, right, to let's say a tree, right? Tree's organic, it's complex, it is what it is, maybe not as complex as who we are, right, in terms of our ability to do what we do. This is just the beginning of where we're going in terms of new energy. So, as I said earlier, when you look at orange printed semiconductor and you think about where you had zeros and ones, think about you only had zeros and you only had ones. What is the door that opened? The door that opened is now we have quantum mechanics at work for orange materials. So our orange printed semiconductor is now taking advantage of what happens in quantum mechanics. And so when you think about AI systems, they're doing quantum computing, right? They're now able to solve equations because it's no longer zeros and ones. They can solve all the equations between zero and one. Think about us in terms of now what we're going to be able to do in the energy space and the fact that we're working in the same quantum space of quantum mechanics.
Okay, so when you say like quantum mechanics, I know when you have like photons, that would be a quanta, like, things you can't break down further. How does that relate? I mean, I'm not a quantum mechanics expert.
So what you end up having is that when you have the nanoparticle,
So nanoparticle, that's like an individual atom, I guess.
it's basically what we were talking about before. When you discovered the fullerene and you
Hmm.
created that then is a nanoparticle. So it's something
Hmm.
that you can't even see. In that space, you're now in this position where your electrons are matching where you're getting one that's spinning one way and then your other electron that's spinning the
Uh-huh.
other way. It's called the Pauli principle. And so I did not invent that. But it puts you in a place where what you're now able to do with the movement and the activity of electrons is well beyond what you could traditionally do in zeros and ones.
Okay. Well, cool. I think maybe that might be a little bit above my pay grade right now. So once I become at one with my AI, though, it will be real easy to figure out. Another thing about this, too, is it's transparent. So I guess that means bifacial because light can come from both sides.
It's exactly right. So it's bifacial. The printing is exactly the same. It's singular. So you were able to use light from both sides. Effectively, what the new shade is going to do is open up the ability to, I would say, redefine the real estate industry. So for right now, we're only doing it in commercial. At some point, obviously, we'll enter into the retail market. But the idea that you're correct, it's being transparent, we're removing 100% of the glare that's coming through the window. The purpose of the dual roller. So if you think about a traditional dual roller, you'll have maybe a beautiful fabric that's in the front of a shade, and then the back end of that shade would be that blackout. So when you'd be in a room, you'd be able to have a blackout, or if you're in your hotel, you'd be able to do the blackout. So you're removing all of the light. The idea and the concept was, well, we remove the blackout piece of that double roller shade, and so it gives you the opportunity to now put the orange printed semiconductor next to the window, which is where that traditional blockout shade would be. That's now your power generation. And then you also have the ability to have a beautiful fabric if you want on the front roller for aesthetic purposes. Maybe you want that to match your decor in terms of your furniture, or you want it to match in terms of whatever else is happening in the environment. So that's the coolest part about the relationship between Mecco and GO-OPV Orange has been that the engineering behind the utility of the shade is doing so many different things. And one of those features is Mecco's solar track. And so as you were talking before that I had a button underneath in order to operate the shade that I was actually showing you, that can now all be automated. So an entirely automated system using Mecco's solar track enables you now that you never have to do anything. So not only do you not have to wire up the shade, but once the solar track system is integrated into using the shade, you don't have to even determine putting the shades up or putting the shades down. Every single thing within the environment would be completely automated.
So do you automate it based on the light or the time of day or both?
It can be three different conditions. It could be time of day. It can be actually the amount of light that is entering into the window. And you can actually do it based upon how much heat.
Okay, great. So you have temperature sensors.
We can have those. Yes,
Hmm.
exactly.
I know that there's some companies out there using non-silicon PV technology, and they're working together with the silicon companies and making like multi-junction solar. Are you looking into any of that or not?
Yeah, I think in terms of what we're doing is related to how far can we take nanotechnology, how far can we take quantum mechanics, and how can we do this in what we would refer to as a flexible film or flexible substrate-based system. So for on the PIN side, what they're doing in what you call traditional silicon, it fundamentally doesn't really relate to what we're doing because our path is entirely different. And so when you look at where fossil fuels were and you look at where we are now, that we're able to use that in a way where you have zero emission and you're able to use the complexity of what an organic structure involves, the path to where we're going is well beyond, a simple pin, PIN structure.
All right. So another thing I was going to ask is since it's organic solar, is it alive? Does it have consciousness?
Not yet, but you never know, right? You never know.
Yeah, and I guess sometimes some people think that consciousness comes from like quantum mechanics or something like that. So,
Yeah, so I find it intriguing that where we're going in terms of the quantum space and the fact that we're now dealing with orange printed semiconductor, and now we're in that quantum space. You look at the basic computers and you say, okay, so we had the calculator and we have our laptop. I mean, I think that's all pretty sophisticated stuff that's built on, traditional semiconductor. But then when you introduce, the high-end quantum structure and you see today the competition in the market in terms of the processing power. When you just compare the processing power in the quantum space versus the non-quantum space, it's so exponential, no one can even compare it. When you compare that for us doing that in the energy space, who really knows what you want to do? Because within the printing process, we're now able to print diodes. We're now able to print all kinds of electronic structures within the orange printed semiconductor that will now be developed over time. So, right, our original process was, okay, we need to be able to do this. Now, from this point, it moves forward. And I think the answer that I'm just running on with the sentence to explain it to you is why did no one else do it? Right? That's sort of the big question. Why did Kodak and Polaroid not get there? The answer is that in the nano space, you needed to be able to match the electron. So you needed to be able to match. And so when you're doing roll to roll processing, I always enjoy this. You went back to chemistry. Think about geometry. When you go back and you look at a roller, and we're using conventional print processes, no one realizes that the diameter of the roller is by pi. So think
Mhm.
about that. You now have the diameter of a roller, and that's now by pi, and you're doing this in a continuous printing process. And let's say that you're doing it over 5 different heads, right? What is the probability that you're going to end up matching all of those electrons at the nano level? That's part one. And part two is the interesting part about, at the time, fullerene, is that fullerene will absorb all of these electrons until you introduce moisture vapor. So if you introduce moisture vapor, you introduce water, the interesting part about fullerene is it stops absorbing electrons.
Hmm.
It goes into a totally stable state. So that's what happened in 2018. Our company, GO-OPV, was able to eclipse what we referred to as the climate chamber test, where you infuse an enormous amount of water vapor. You do it at a very high temperature of either 65 C or 95 C. And so at those levels, all other organic printed semiconductors failed. They failed because the water vapor was able to reach the fullerene. Once it reached the fullerene stopped accepting electrons. And so essentially you had a dead system. And so we overcame that in 2018. And then, as we discussed earlier, we were able to create a distribution network with the storage, with the batteries and the PoE. And then we did 5 years of field test. And so we've been field tested for 2 years since 2022. And the big movement was the General Services Administration in 2023, as well as the installation at ASHRAE. ASHRAE being the American Association of Heating, Air Conditioning. And so these are parts that most of the market is not aware of all of this work that's been done in order to bring us to this point.
So I was wondering too, like, about LEED buildings and LEED Platinum and all that. It's just like energy efficient buildings. And you get points for different things. So one of the things you get points for would be putting solar on your building, and another one would be for being energy efficient for blocking that sunlight just for going in and heating up the building. So maybe you get double points there.
Yeah, you're going to get double points. And one of the biggest things is, and we don't know where the administration is going to go in terms of the IRA credits, but every single orange electric shade is going to be eligible for 30% in
Sure.
terms of the ITC credit. So all of those features that you're talking about, meaning, okay, you're going to get LEED certification, you're going to get, potentially an IRA credit, you're going to get into this new technology that, unlike traditional silicon, you need 20-year paybacks, right? You need 13-year paybacks. So people say, well, what's it going to cost, right? A traditional orange payback is between 3.5 and 5 years because of the ability to do the heat gain reduction. We have so much savings relative to the heat gain that the paybacks are significantly accelerated.
Okay, great. And I think kind of too, with the name of your product being orange, the new administration's not going to shut you down. But another thing is about a little bit about computing and quantum mechanics and stuff like that. So you've got solar cells that are made out of silicon, and they're very similar to computer chips. How about, are you printing quantum computer chips?
Yeah, so there's a great book that is out in terms of how organic printed semiconductor works. And that's exactly correct. You can now print different types of systems through printed semiconductor that we're now doing carbon-based. So non-fullerene, and now you're going to be able to print sophisticated electronics in addition to the simple PINs that we're doing today. So imagine this is the beginning of something that was never doable before because no one was actually able to print and encapsulate the material properly for it to be commercially viable. And now that we have that solution, all of these things that we thought are possible, as you would compare them to, okay, if we could just do the quantum computer, we could do all of these things. We now have quantum energy, right? We now have nanoparticle energy. And so really, who knows where the future goes?
Pretty cool. Well, I'll be pretty excited about that. And so also thinking just a little bit about like there's, a lot of talk about tariffs and things lately. Are you manufacturing in the US?
So every component for the manufacture of the material either comes from the US or in North America. And then all of those materials are actually shipped to the one printing plant that we have, which is in Brazil. And that's my partner and co-founder, Felipe Travesso, who handles that. And so we have one printing press so far in the world. And so the goal is under the CHIPS Act, the new CHIPS Act for the semiconductor, our real goal is to build our second plant in the United States. We've actually identified in Florida, which is where the company is headquartered in Palm Beach. Our goal is to build the largest printed semiconductor plant in Indiantown, Florida. And through NREL, all of the research and all the documentation in order to build that plant is all set up. And so part of what we're doing now is raising the funding in order to do that. And so introducing the new shade and other products that we're going to be doing, our goal is to make it viable now that in terms of policy that the US government wants to follow, especially in semiconductor, this is a perfect opportunity for us now to move forward on both fronts. One, that we're fossil fuel based, but zero emission, which is great. The second piece is that the country wants to move forward in being the dominant semiconductor producer in the world. And what better way to be that in printed semiconductor?
That's pretty cool. Yeah, I just went to a factory in Indianapolis last week that they're building. They're almost done. They've made some modules over there. And so I know that a lot of the manufacturing going on with solar, they're still getting the cells from places like China because there's not really much in the way, if anything at all, at least on any decent scale, of solar cell production in the United States, except for maybe First Solar. And so it sounds like you're planning on making some cells in the US.
So we're actually not going to make the cells. We're actually going to print ink. And so when you think about it, okay, so we're going to leapfrog,
Uh-huh.
China completely. We're
Uh-huh.
completely 90% of all the silicon wafer that comes in from China. We're just going to leapfrog right past that. Imagine you having your landline that you used to have all the time, and now you've gone to cell phone. When you think of orange printed semiconductor, we're the cell phone, right? We're going to
Mm.
completely leapfrog past all of that embedded historical traditional infrastructure that you no longer need any longer. You don't have to do any heating of the sand. You don't have to do any cutting of wafers. You don't have to do any of the assembly of those panels. We're literally going to take ink, we're going to print it on PET plastic, and we're going to make zero emission power from carbon.
Okay, so you don't even call it a cell, like a solar cell. I think like in the NEC, they might define something as a solar cell. It's like the individual power producing unit or,
Yeah, I mean, they'll refer to it as an organic solar cell if you
hmm
want, but the reality is that you're printing in
hmm
roll-to-roll form ink. And so the roll-to-roll, you normally print them today in about 100 square meters at a time. And then that continuous roll is then made into sheets. And then those sheets are shipped to the US for final assembly for their junction boxes.
from Brazil, which is America. Yep, South America.
Yeah. And so the idea is that if we produce this now in the US, we put the printing plant here in the US, we already have all the materials here, all the PT, all the junction boxes, everything is already here. We're going to reduce the cost by 70% because there's no shipping and there's no secondary processing. And so our capacity today is about 30 megawatts. The target is to produce the first plant with 240 megawatts.
Wow.
Uh, so yeah, this is the real deal.
Okay, great. Well, I'm pretty excited about that. And once again, what part of Florida are you located in?
So we're in Palm Beach, Florida.
Okay, Palm Beach, a
Yeah,
very, very orange place. Like,
very orange place, and we are looking to hopefully put our first plant in somewhere near Indiantown, which is about 40 minutes from where we are. But obviously open to any other opportunity where people are interested to be the leader in what we think is going to be the future of energy.
great. It's a nice place down there. I did spend a few months quite a while ago in South Palm Beach, so right next to you
You would have
there.
been right down the street from me.
Uh-huh. Yeah, I'd like to go back. It was some good days over there. So, yeah.
Yeah, and I think, where we're going with this in this conversation is that the fact that we're able to ship film from the printing plant in Brazil to the US, where I'm driving with this is that we can also be the largest exporter of power in the world. So when you think about the fact that we're going to be able to make zero emission power from flexible PET, that can be shipped anywhere in the world. So the same as that we're exporting our oil around the world and our liquefied natural gas, we're going to be able to ship around the world and be the largest exporter of power in the world. Because when you look at countries like the Ukraine right now, Ukraine's grid is being blown up every day. Think about orange printed semiconductor, you ship boxes of that there. You can turn on the lights all day. You can take a standard car battery, you can store the power. The interference to the grid is going to be reduced. It's incomprehensible to think about how much we're going to be able to do with orange printed semiconductor because you have to get yourself out of the frame that you know what this power source is. You
hmm
have to get comfortable and say, I've never seen this power source before. I don't fully understand this. I know how solar works. I know how wind works. I know how fuel cells work. I've never seen this before. And that's the driving force. And we expect with the shade and continued installations. I will give you one other story if you want. So we were installed at the General Services Administration in 2023. It was called the Working Innovation Lab.
And where was that?
It was called the Working Innovation Lab.
In what city or state? Is
It
it?
was in Washington, D.C. It was in the headquarters. It was 1800 F.
Okay.
And it was a test in order to see whether or not what we were producing in a low voltage DC environment with orange using power of the Ethernet would be much better. How much savings would there be relative to the other side of the building, which was 12,500 square feet? We were in 12,500 square feet. And could we make power on the second floor inside Washington, D.C.? And we were actually making 18 kilowatts per month, saving the installation for all of the lighting by 25%. We were reducing the temperature within the floor by 6 degrees, in some areas, 8 degrees. And it was so successful that we were awarded the retrofit of the Department of Transportation building in order as an energy conservation measure, which was awarded to us in January of 2024. And so now the question will be is, how serious is the federal government about retrofitting the 300,000 buildings that were now qualified to use power over the Ethernet? Because part of that platform was all the power was done power over the Ethernet. And the Department of Transportation that's already been vetted and in theory funded, that we complete that installation as an example for how all federal buildings, which there are 300,000 of them, can now be new efficient buildings.
Great. That's pretty awesome. So I know the name of your company is GO-OPV. That's GO-OPV. And then the product is you're calling orange, and it's capital O, capital R, capital E, capital N, small g, and a capital E. So what is the orange referring to?
Right. So when we first opened the company, we were looking at what was considered at the time organic PV. So it was, Go, organic PV. And then we really started getting into non-fullerenes and other constructed elements. And so we realized that it's really organic energy. And so we realized that in order to brand this, we needed to be sort of like what Kleenex is relative to facial tissues, right? Everyone
Mm-hmm.
walks around and they say, oh, here's a facial tissue, but then you really refer to it as Kleenex. And so
Sure.
the idea
Yeah.
is that if we're going to be in the organic printed semiconductor business, we need to have a good name that relates to organic energy. And so we fundamentally came up with the term orange.
Okay. And the term orange, does that stand for things with the different letters or just organic energy, pretty much?
It just stands for organic energy from the
Cool.
standpoint that that was how it was created as our logo and a way to trademark it relative to the films that we're producing as printed semiconductor. And we really think this is going to be an exciting era.
Well, awesome. Let's see, is there anything else that we didn't cover that you would like to talk about? And we can also do this again too if you wanted to, especially after you're pumping out the megawatts over in Florida.
Yeah, I'm very excited. I'm really appreciative that we're doing this conversation, Sean. It's an opportunity for us to make people aware who have never seen organic printed semiconductor. It's just something that you can't imagine. So, one of the points that I like to add is the shades are intended to be dealer installed. And so, what will happen is that there'll be a dealer network in collaboration with MECO so that those dealers who have the ability to do the installs for the electric shade system and are also predominantly POE rated will probably be the first link in terms of who's going to be able to get these shades. The shades are going to be available obviously this year, but there'll be a lot of discussion as to will I be able to see the shade? The shades will be available for demo at each of the selected dealers. And then that'll sort of be the beginning of the rollout for the orange electric shade.
The rollout as the shades roll out. And then I know that I have odd shaped windows. Will that work? Do you cut them individually for different windows?
So the nice piece is we can actually cut them for different things, but the initial market is the commercial market, and you sort of have your standardized structure. So when you think about it, we move from brick and now we move to glass, right? So
Mm-hmm.
now we now have these very large skyscrapers with an enormous amount of glass, which obviously has glare and a lot of infrared, and why everyone has a shade in terms of blocking the sun, right? In terms of the glass. What the shade's going to be able to do now is you can take exactly the same shade pocket. You can now use the mechanical structure of the electroshade. You have the film that's already going to come with that. And so to do a retrofit is going to be what we think is going to be very simple in order to do that. And those windows are standardized. You have standardized
Oh,
48
okay.
inch, you have standardized 60 inch. And so each of those window frames are all standardized in the commercial market.
Okay, great. All right. Well, thanks so much, Paul Frischer. And where do people get a hold of you or find you or your company? Yep.
You get a hold of me at Orange Power. There's a contact form there where you can get in touch with me. You just send me, and I'll be able to retrieve that and answer whatever questions that you have.
Awesome. And we'll put all that information in the show notes. So thanks so much, Paul Frischer. That's an Frischer. And that's of GO-OPV. That's GO-OPV. And we're talking about these orange solar cells. So thanks for listening. And in the future, if you want to get educated about solar and storage, go check it out at Solar, SEAN. That's solarshawn.com. I'm also going to be teaching the NABCEP PV Associate class at the NABCEP conference, and that's going to be in Reno, Nevada towards the end of March. See you there.